Okay, so yesterday we did a lab. Did you guys enjoy that one? Most kids usually do because like you have to watch stuff blow up and light on fire and do cool things, right? You weren't here. It was a bad day to miss. I mean, if you want, I could find you some YouTube clips of other teachers who've done it too. But usually the reactions lab is kind of fun. The goal behind it, though, the reason why I do it is one because I want to show you that chemistry can be cool, but two, the main goal is I need you guys to know the examples of what makes a chemical reaction. What are the things we're looking for? And I've got a slide here that just starts off by reminding us the two kinds of change. There's physical changes and chemical changes. Physical changes are things like when you freeze water. Is it still water when it goes from frozen to solid? Yeah, it's the same thing. The big difference between the two is this word right here. A physical change is reversible. You can undo a physical change. Right? If I freeze water, well, I just melt it. Now it's back to where it started. But think about some of the reactions I did yesterday. When I blew up that gummy bear or that jujube and it like lit on fire and blew off the pink sparks, can we get it back into its jujube form for us to eat again? No. Yeah. Rhetorical question. Obviously not, right? Chemical changes involves something new. And so my goal yesterday was to help you be able to visualize some of the really common things that cause chemical reactions. Um, the term that's the term we're going to use here is chemical reaction. Okay, when something changes, we call it a reaction. Okay, the key here is there has to be a different substance. We have to make something new. Water freezing is not new. If I were to crumple up a piece of paper, that's a physical change, but it's still paper, right? If I were to put some cereal in water, is that a chemical or physical change? Because all I got to do is evaporate off the water, and eventually it'll dry out again. Here are, though, some examples of some ways that we have chemical reactions. Let's talk about our lab from yesterday. All reactions should have new substances with new properties like state of matter. If all of a sudden now there's a gas, and there wasn't one before, there's something new, right? Or if there was a solid that came out of nowhere, then that changes. Or what happens if there's a new color? What if there's a smell? Those are some things that we noticed yesterday, hopefully, in the lab. It's a little harder to measure density and melting point, but really, as long as a chemical property is different, a chemical reaction took place. Here's another thing that we might have noticed on some reactions. Energy. Often there's temperature changes. There were about 3 or 4 reactions which clearly gave off heat because like something exploded or lit on fire, right? There was actually one reaction where it got cold. Do you guys remember that one? Some of you actually felt the bottom of the beaker where if it doesn't get warm, some reactions actually get cold and they go the other way. They absorb energy. Here's another thing. I've already mentioned it up here before, but any sort of phase change like gas or solids, that would also be good indicators of chemical reactions. So yesterday in your lab, it was a pretty easy task. All I needed you to do in your results is just write down what you saw, right? And as long as you were thorough, and here's a really key thing though, you need to be organized. Okay, if I can't read your work, I can't give you marks. So some of you on like the previous lab I passed back didn't earn full marks. A lot of times it's because I wasn't able to follow what you did. So make sure it's organized and maybe have labels and say there was a phase change. Dash. We saw a gas. There was a color change. Dash. It went from white to yellow. Right? Like make sure it's organized. Okay. But really, that was the goal of my lab yesterday, is to make sure you guys could observe changes. Okay. Today I'm going to talk about some more theory here, and I want to make sure you guys use the right terms. The 2 words I want you to underline here or highlight are reactants and products. Reactants and products. Okay. A lot of kids, they are able to figure out what a product is just based on the root of the word. A product is something that is produced. Product, produce. So when you produce something, that's a product. It's what you have after you're done. After a reaction takes place, what you're left with is a product, whereas a reactant is what you have before. And really, if the chemical properties change from before to after, then you have a chemical reaction. For example, let's take the jujube one, right? Before we started, we had a jujube. That would be a reactant. The reactant is what you begin with. When you're done, when it's finished, the product is what it turned into. It turned into charred black ash mess. I had to throw out the test tube because it was totally burnt up. Does that make sense? So products are what you produce. Reactants are the things that you react. And what I need you guys to know is that we often write them in formulas that look like this. Now, this is really the extent of Science 9. We don't go a whole lot further than this, but you need to be able to look at this and be able to tell me what's happening. So there's a lot of information going on here. The first thing I need you guys to be able to do is look for an arrow. An arrow is what separates a reaction. Because on this side of the arrow over here is what you began with, and on this side of the arrow over here is what you made. So if we're using the proper terminology, the stuff that you begin with is known as reactants, and the stuff over here is known as the products. So really there's three pieces to any chemical equation. There's the beginning piece, the things you react. There's the arrow, which separates it, and then there's the second half, the products, the things you make. Ideally, you guys should be able to look at a chemical reaction and know a few things involved. Like, for example, I would expect you guys should be able to name that compound. That's water, right? But I would even expect you guys to be able to name this compound here too, because we've talked about how to name stuff like NaCl. This is sodium chloride, which is salt, yeah. But I mean, you might even be able to name the things on the other side here too. Now, that's not actually my goal right now. I'm not really focused on naming today, but it's something you should be able to do. My goal today, though, is can you look at a chemical equation and kind of know what's happening in general? There's stuff on this side. There's stuff on this side. There's an arrow in between. We call that an equation. It's kind of like in math. You guys do a little bit of algebra in math, right? Where if I said 4x plus 2 equals 8. You guys ever come across an equation like this? Right. This right here would be like your reactants. This would be your products. And this is kind of your in-between sign. It's very similar chemistry to math. Okay, I want to go back to a scientist that we've talked about earlier. His name was Anton Lavoisier, and we're going to talk about his contributions for a second here. He realized that when doing experiments that the mass that you started with, if he weighed everything that was considered a reactant, and if he weighed everything that was considered a product, he realized that whatever you started with always equaled what you finished with. And we actually give a name to that. We call it the law of conservation of mass. It's actually what we're going to do in our lab on Thursday. We're going to test it. I'm going to give you guys, actually you guys are going to go and you're going to weigh out some reactants. You're then going to combine them together and make products. And you're going to weigh what we start with. You're going to weigh what we finish with, and we're going to see whether really it is true that if you start with 5 grams, you end with 5 grams. And I've kind of got like a picture here to kind of illustrate it on this slide here. Imagine that you started with 13.9 grams of iron and 8 grams of sulfur. Well, 13.9 plus 8 equals 21.9. According to Lavoisier, whatever you start with as a reactant should equal what you finish with as a product. So we're going to test that on Thursday and see whether we can actually prove that to be true. The only thing we really need to do is just be really meticulous in measuring things when we weigh them on the scale. So I'm going to try to take myself out of the way and actually have you guys do more of the work now. So I think the best way for this to work is that I'll probably call you guys over in like say groups of 4 to 6 or so, and then I'll just set up the back table there. And we'll let you guys each kind of do it one group at a time. Okay. So usually what I end up doing with in my labs is I usually let you guys choose your own partners. So we'll play that by ear on Thursday. If you guys can come together with like a group of 4 to 6 on your own, that's fine. If not, I don't really care. We'll make it work somehow. So I don't really want to assign groups. So, okay, here's another thing I want to talk about though is how this applies to these chemical equations. Because really what happens if we break it down to a molecular level is that there were a certain number of each particles before we started. Right? See these guys right here, they're white right here. How many individual white I don't even know what white stands for, but how many were there? There were 6, right? 1, 2, 3, 4, 5, 6. Well, look, afterwards, there's still 1, 2, 3, 4, 5, 6. Yeah, they're just not together. How many blue ones? Well, there's 1, 2, 3, 4, 5, 6 individually, but now there's still 1, 2, 3, 4, 5, 6. Only these guys are now a compound. No, blue, purple, whatever it is. Okay. But really, at its molecular level here, this is what's happening. And so whatever mass you have here, it should be the same mass that you have afterwards, because really, you have the same stuff. It's just in new spots. Let me say that again. You have the same stuff. It's just in a new spot now. Okay. We actually have a way of showing that in our equations as well. And I want to use this really basic example right here to talk about this. Okay. This right here is hydrogen gas. And I've mentioned before the idea of an allotrope. Hydrogen always comes in 2s. Remember that little 2 we put in the corner there? There's actually, hydrogen comes in packages of 2. And right here, oxygen also is diatomic. It comes in packages of 2 as well. Well, let's say that hydrogen and oxygen come together to form water. That's a very common reaction where here's my reactants, here's my products. But I want to count out what we see here. Count this out here. I've got 2 hydrogens, so H and H. I've got 2 oxygens. Well, now when I'm done, I still have 2 hydrogens. Remember how this 2 applies to the hydrogen? But there's only 1 oxygen. This is a huge problem. How can I start with 2 hydrogens, end with 2 hydrogens, start with 2 oxygens, but end with an oxygen? Where did the other oxygen go? It can't be lost. That would break Lavoisier's conservation of mass idea. And so what we often have to do is something called balancing an equation. And here's how that would look. Okay. If you see an equation, sometimes there are numbers written in front of formulas as well. Sometimes there's the little numbers down here. And this tells you how many of them there are in an individual group. But sometimes we put a big number in front as well, and that tells you how many of the compounds you need. For example, here's what actually needs to happen. We need to have 2 groups of hydrogen gas. But hydrogen, this 2 right here, means that each group comes in a pack of 2. See how this happens here? This 2 means each hydrogen comes in a 2-pack. Okay. But this 2 right here means we need 2 2-packs. How many hydrogens do we have now? 4, yeah. Now, this oxygen right here also comes in a 2-pack. So right here, here's your oxygen in a package of 2. But how many do we need? Well, just 1. And in a way, it's almost like we write a 1 in front of it, but we often don't bother writing the number 1 because it's kind of silly. In the same way that if you talk about x and y and 2x, sometimes we can write like a 1 in front of those, but like it's kind of silly to write the 1. So really, this is a recipe. If you have 2 hydrogen molecules and 1 oxygen molecules, it makes 2 waters. Because again, water means you need 2 hydrogens connected to 1 oxygen, but this 2 right here means you have 2 of them. That's what these numbers, if you ever see them, refer to, is it refers to how much you have. Now let's count things up. We have 1, 2, 3, 4 hydrogens, and afterwards we have 1, 2, 3, 4 hydrogens. Before we had 2 oxygens, afterwards we have 2 oxygens. And so this is called balancing. Now, I don't need you guys to be able to balance equations, but I need you to be able to look at an equation and figure out what the heck these numbers mean, because there's really 2 of them. There's the small subscript numbers, which tells you how many is inside of the molecule. And then there's this coefficient in front, which tells you how many of those molecules you need in a reaction. So let me show you another common one here. This is the combustion of methane. And it works like this. Here's the chemical equation down here. It involves taking 1 methane molecule. What is a methane molecule made of? Well, it's made up of 1 carbon and 4 hydrogens. Then you need 2 oxygen molecules. Now, oxygen comes in a pack of 2, but you need 2 of them. Okay? So that's why there's 2 of them drawn here. When you're done, it makes 1 carbon dioxide, which involves 1 carbon, right here, attached to 2 oxygens. See? And then you need 2 waters. Water is 2 H's with an O, two H's with an O, but you need two of them. And this is balancing because now we should have the same things before and after. Check this out. 1, 2, 3, 4 of those. 1, 2, 3, 4 of those. Here I need 1, 2, 3, 4 of the red ones. On the other side I have 1, 2, 3, 4 of those red ones. And then finally I have one black one here and one black one here. Let's say though that I didn't think I needed two of these. This would then break Lavoisier's conservation of mass because it wouldn't equal, it wouldn't balance each other. And so that's what these coefficients mean. So one last time, I think I've said this like 5 times. I need you to know what the big number in front means. The big number in front means how many of that molecule you have. So this 2 in front means you need 2 oxygens. But these little numbers right here tell you how many of them are in the package, I guess. So oxygen comes in a package of 2. Carbon dioxide comes in like a package of 3, 1 of these and 2 of these. 1 carbon, 2 of those. So what I need you guys to be able to do is if you look at a chemical equation, I need you to be able to tell me how many total oxygens or carbons you might see. Okay. I think I'll leave that there. Okay, last couple of thoughts here. I need you to know a couple of more terms as well. All reactions either need heat or they give off heat. They either absorb energy or they give off energy. We actually saw both of these in our lab yesterday. A lot of our equations, they lit on fire, like the test tube that was like exploding basically, right? This would be an example of what we call an exothermic reaction, where it releases energy off. Energy is given off. Now it can be light or heat or electricity or sound, but somehow there's energy being given away. Usually that's like because it explodes. But there's another kind of reaction I need you to know about. It's called endothermic reaction. And these are ones that absorb energy. And usually what ends up happening is the reason why they absorb is because they feel cold. When you feel something that's cold, it's not that cold somehow, how do I put this here? Cold doesn't exist. Cold doesn't exist. Cold just means that there's an absence of heat. Cold doesn't exist. Cold just means there's an absence of heat. Dark doesn't exist. Dark just means there's an absence of light. Yeah. So in a way, what was that? I don't know. New way of thinking about things here. Let me say that again here. I think this is actually poignant. It's worth saying here. Really, there's no such thing as cold. Cold just means that there's no heat. There's no such thing as dark. Dark just means that there's no light. Okay. Well, when it comes to cold, what you're really feeling when you feel something cold, you're feeling the heat leave your body. Does that make sense? When you are cold, it's not that the outside air is cold so much, it's that there's a lack of heat around you. And when you feel cold, heat is leaving your body. Does that make sense? Whereas when you're getting warmed up, heat is entering your body. If you stand by a fire, that heat warms you up. But when you're feeling cold, it's actually you giving away your heat to the environment. Well, that's actually what naturally happens. So when you have a cold pack, anyone ever used one of these cold packs before? Where you like crack it and then you put it on your knee because you sprain your knee in basketball or something? Perfect. Okay, so you have experience with this. Okay. Here's what I need you guys to be able to do. I need you to be able to look at a chemical equation and figure out what's happening, but also know whether it's either exothermic or endothermic. Exothermic things give off heat. They release heat to the environment because they are warm. Endothermic things, they're cold. But since I just told you that cold's not really a thing, what really happens here is a cold pack actually absorbs your heat. When you put a cold pack on your knee, it's absorbing the heat out of your knee, and then you feel cold because you are losing heat. Does that make sense? So let me say that one more time, and I want to add one more to the list. There's really no such thing as cold. Cold is just the absence of heat. There's no such thing as dark. Dark is just the absence of light. I like to kind of keep this analogy going when it comes to my students. There's no such thing as stupid kids. There you go. Yeah, it just means you haven't learned it yet, right? I don't want anyone to ever say, or for you to ever say that you are dumb or something like that. It means you haven't learned it yet. That's all, right? In the same way that There's not dark, it just means that there's no light here yet. It's not cold, there's just no heat here yet. Guys, I really sincerely mean this. It just means you haven't learned it yet. That's all. That's the whole point of school. So, anyways, I digress. That's not really my point. That's not what I said in the slightest. I just said that if you don't understand something, I think it's important to know that you just haven't learned it yet. That's all. There's just a lack of knowledge, but we can help fix that. Okay. Here's the words I need you guys to know, though, because I'm getting off topic here. Exothermic, endothermic. Here's one of the ways that I remember the difference between the two. Exothermic is like it exits. Energy needs to exit the system. Heat is being given off, usually because there's like an explosion. It warms you up. Whereas endothermic, it needs to enter. You need to absorb the heat. This cold pack right here isn't really cold. It's just lacking heat. And so it's going to absorb heat. Where does it absorb it from? You. That's why you feel cold. Does that make sense? Cold does not transfer. Heat transfers. Light does not transfer. Or darkness does not transfer. Light transfers. Right? In the same way, knowledge transfers. All right, let's move on. Can you guys look at this equation, though, and interpret what's happening? This arrow right here, it means that that's where the reaction takes place. So here, we're going to start with a chemical. It's going to absorb some energy, and when we're done, here's what it produces. You should be able to look at that and kind of interpret what everything happens to be. These are the reactants. These are the products. So here's a slide that more or less summarizes what I just meant here. If it's exothermic, energy exits. It gives off energy. If it's endothermic, energy enters. It absorbs energy. Okay. So one of the questions I had on your lab from yesterday then was, go back through our equations and try to tell me which ones were endothermic and which ones were exothermic. There was only one endothermic reaction. It was the one where I poured those two solid chemicals together, stirred them up. It stunk really bad. But remember how you put your hand on the bottom and it felt cold? That's because it was an endothermic reaction. It was absorbing energy. Anything that lit on fire or exploded or gave off light or sound or heat, those are all exothermic because energy was being released. Okay, last thing, and then we're done. The last thing I need you guys to know about in this unit, and then we really are finished a whole unit, is I need you to know about a couple of common chemical reactions. There are millions. I already showed you like 9 yesterday, but here are a couple of common ones you should know. Combustion, corrosion, photosynthesis, and cellular respiration. And I promise you, you guys have experience with all 4. You might not know it, but you've experienced all 4. So here's the first one. This is combustion. Combustion is like basically whenever something blows up. If something explodes or blows up, we consider it combustion. And in order for something to combust and light on fire, really there's 3 components. And I have this little triangle thing here. Have you guys seen this before at some point? In order to light something on fire, you need a fuel, you need heat, and you need air. Right? That's how you light a torch. That's how you light your barbecue. That's how the engine in your car combusts fuel. Okay? So this would be a really good example of a combustion reaction. You're going to take some of this molecule here, which is the fuel. You're going to take some of this molecule right here, oxygen. Oxygen is really the main component we're getting out of air. And then it's going to produce these products right here. So here's your reactants. Here's your products. Here's what I might need you guys to be able to do. Can you tell me the purpose behind this 6 and this 14 or this 12? Do you get the difference between the two of them? The 6 right here means that this molecule right here comes with 6 carbons and 14 hydrogens all together in a molecule. This 2 right here means you have 2 of those carbon-hydrogen molecules. So here's a question I might ask you then. In this molecule right here, say this one right here, how many oxygens are there in that molecule? Total. How many oxygens are being shown right here? That's just 24, yeah. Individually, there's 2. Right? In each one of them, there's 2, but you have 12 of them. 2 times 12 is 24. Anyways, this is one kind of reaction I want you to know about. Here's another one. It's called corrosion. Really, corrosion is another fancy word for rusting. When you see something rusting, It's corroding. And it basically occurs when oxygen causes something to turn into a compound. Here's another example of a chemical reaction that you might have to interpret. Here are the reactants. Here are the products. Let me try another example here. How many oxygens do we have right here, total? The answer is 6. This individual molecule comes with 3, but we have 2 of them. So really what you have is 2 irons attached to 3 oxygens, but then you have a second 2 iron group attached to 3 oxygens. So how many oxygens do you have total? 1, 2, 3, 4, 5, 6. Okay. So that's rustic. That's another example of an equation you've probably seen before. Here's a third one. It's called photosynthesis. Okay? Plants use photosynthesis. They actually absorb light from the sun. And I want to point this one out because this one here is endothermic. Okay? Combustion. When you blow something up, it gives off heat. Right? If I were to light a wood on fire, when it's lit on fire, it gives off light. It gives off heat. That's exothermic. But photosynthesis is what happens in plants. Plants, you need to water a plant. Plants need air. But you know what else a plant needs is sunlight. And if a plant absorbs sunlight from the sun, that's what causes the plant to grow. And so this is actually a good example of an endothermic reaction where you need sunlight to make this reaction occur. Can you guys see how in this reaction right here, the energy is on the product side? If energy is a product, it's exothermic. But if you need some sort of energy to get this reaction going, like light right here, that's what makes this endothermic. So this is actually what plants do. Plants take light and carbon dioxide from the air, and you also have to water a plant. If you don't water a plant, it doesn't work. And what a plant does is it makes this molecule right here, which is basically a sugar. And that sugar is what makes the plant grow, because it feeds on that sugar. Anybody ever heard of photosynthesis before? It's a term you've heard at some point? Okay, cool. Okay, there's one more reaction type I want you to know about. It's called cellular respiration. And this is actually what keeps our bodies going. Okay. You eat food. Hopefully you've eaten breakfast at some point, or you've eaten at least, right? Well, your body will now take that food and convert it into energy through this reaction. This would be an example of a sugar. Now, as humans, we need to eat. But we also have to do one more thing. We have to breathe. Okay, if you stop breathing, you'll also die, right? You need to eat, you need to breathe. But in the air, the reason why we need air is due to oxygen. We need oxygen to combine with our food. The sugars in our body and the oxygen we breathe will actually give us energy. So quick question here. Is this an endo or exothermic reaction? As humans, does our energy get released into our bodies, or are we absorbing it? This one right here, this is exothermic. Look, we start by taking sugar in our body and add it to oxygen, and energy gets released into our body so that we can go run around and do stuff. So if you ever see energy on this side over here, it's exothermic. But if you ever see energy on this side over here, it's endothermic. You need to absorb. So plants absorb light. They're endothermic. We as humans, when we eat our food, that food combines with oxygen and gives us energy. Now we can use that energy. By the way, you might already know this, but when you breathe in oxygen, what do you breathe out? Carbon dioxide, yeah. You actually have to breathe out carbon dioxide. And one more thing, you know what else it produces in your body? Water. Which makes sense because you need to go to the bathroom sometimes. Sometimes we accumulate too much water in your body. Right? It also has to get rid of other impurities too. But this reaction actually makes a lot of sense. So one last thing, and then I'm going to be done for the day. I need you to be able to look at this equation and interpret what's happening. These things over here are reactants. These guys over here are products. I need you to know what this 6 means, or this 2 means. The 2 means that individually, water has 2 hydrogens and an oxygen. But collectively, we need 6 of them to make it work. All right, last slide. Then we're done. I'll stop talking. Some of these reactions happen really quickly. For example, combustion and cellular respiration. When I breathe in, that just gave me energy. It happened just like that. I now have the ability to keep moving. Okay. If I were to stop breathing, my body can only survive for like 3 minutes without oxygen, and then like my brain starts to shut down, your body functions start to shut down, right? So it's actually really good that some reactions happen fast, but there's some reactions that are really slow. It takes a plant a long time to grow because it has to absorb light really slowly but surely over time. It takes like 100 years for like a small little tree to become one of those big massive trees that's like 70 feet in the air, right? Corrosion is also really slow. Things don't rust overnight. It usually takes a while. So the last thing I need you to be aware of is the term called reaction rate. And it literally is like you'd think, reaction rate. How fast is the rate that a reaction takes place? I mean, there's slow, there's medium, there's fast. So there's actually 4 things that can contribute to something going faster or slower. I want to talk about those, then I'm done. So try to give me 2 more minutes of attention, okay? Here's the first one. Concentration of reactants. Think back to our lab yesterday. When I put the sodium in the water, when I first did it, I put a little piece of sodium in because I was a little afraid of it blowing up. That was not very concentrated. It was a very, very small amount. But what happens when I used a slightly bigger piece of sodium? Well, then that one lit on fire. And I know you joked about it, but what if I put the entire piece in there? It would probably really boom, right? Well, that's reaction rate. The more you use, the faster it happens. That seems logical, right? So concentration of reactants. If you use more, it should happen faster. Here's the second one, temperature. But this one's backwards. We actually use devices to try to slow down chemical reactions. Can you guys make sure you're all paying attention? I see lots of people who are giving me like 70% attention maybe. I see you're on your phone. I'm not going to, you can have it out, but maybe give your best attention. Okay. Freezers and refrigerators. Why do we put stuff in the freezer or the refrigerator? Well, the reason why is that by cooling things down, it slows down the reaction rate. Food molds. You guys have seen moldy food before, right? Well, if you want to slow down the moldy process, make it colder. Because colder things react slower. Warmer things react faster. Colder things react slower. Hence a deep freeze. A deep freeze slows the reaction down to basically with a point where you can keep frozen food in there for years without it ever going bad, right? But if I were to leave like a piece of raw meat sitting on the counter outside in the sun, it's going to be disgusting pretty quickly, right? So temperature is another thing that fixes things. Surface area is another one, okay? If I were to grind things up into dust versus have it as like a chunk, it usually works faster. Let me give you an example here. Let's say you make hot chocolate. Hot chocolate is already ground into a powder. It's very easy then to take that powder and stir it together. But what if hot chocolate were literally like a block? It would take a long time for it to like dissolve. The reason why is that it has way more surface area as a powder. And then here's the last one. It's called a catalyst. I actually showed you a catalyst in one of yesterday's equations. Yesterday, the very, very first thing I did, if you remember, I put soap in with hydrogen peroxide. You remember this one at all? I put soap in with hydrogen peroxide. But it did not react until I put potassium iodide in. And then all of a sudden it spurted out the top. Okay? There's something called a catalyst. And catalysts basically are things that make reactions happen faster. Okay? That's all I need you guys to know because it is way more complicated than that. But for where we're at in grade 9 science, I need you to know what of a catalyst. Catalysts are things that just make reactions take place faster. That soap and that hydrogen peroxide would have eventually bubbled, but it would have taken like years. But by adding the few crystals of potassium iodide, it actually happened fast. So those are the 4 things. Use more, happens faster. Heat it up, happens faster. Or cool it down, happens slower. Squish it up and like grind things into powders. They usually react faster too. Oh, by the way, you know how we need to use food in order to help us survive? One of the ways that our body naturally does that is we chew it. By chewing our food, we break it up into small pieces, and then our body can digest it faster because it has more surface area. If I were to chew an apple and break it up into small pieces, when it's in my stomach, it's broken up into small chunks, right? Whereas if I were to swallow an apple whole, first of all, that wouldn't fit down my esophagus anyways, but it wouldn't digest very well. Does that make sense? It would take a very long time to digest. There are certain animals, by the way, that can eat things whole. Like a boa constrictor snake. It literally can eat like large animals even whole, but it takes them forever to digest because they don't have a lot of surface area. Okay. And then the fourth thing, a catalyst. And all you need to know is that catalysts speed things up. Sound good? Okay, I'm done. Guys, that's our chemistry curriculum. We're finished. So good news now. Good news, bad news. Good news is we have a week. Okay, you're not writing a unit test on this till next week, Wednesday. You have a little bit of time today. You have about half an hour today. You then have all of Wednesday, all of Thursday, all of Friday, all of next week, Monday, all of next week, Tuesday, all of next week, Wednesday. You have a lot of time. But in that time, I need for you guys to prove to me that you can grow and learn from what we've talked about. So there's a couple of labs to do. There's an assignment to do. There's a quiz to do. Eventually a unit test. There's some readings that I want you to do just to read about science. Okay. From here on out, guys, I mean this with love, but I don't care what you do. I do, though. But I'm going to leave it up to you. If you want to just hang it on your phone, I'm probably going to point it out, but that's not a good idea. Okay, but I'm not going to stop you. If you want to, go ahead. What I really strongly recommend, though, is use this time. Engage in your learning. Take part in that learning cycle here. I've now done as much as I can on this. Okay? I've taught you all the knowledge you need to know. But I need you guys to apply yourself, try some of the tasks I give you, do them in enough time to get feedback, and then, here's the real key thing here. Ask me again to help. Okay? My job's not done. The most important part of my job right now is to help you guys get better. So I really, really encourage you to do this. Go over your old quizzes. Go over your old labs. Go over your old assignments. Ask me how you can improve, because that's where my job comes in. Any questions? Okay. You guys have half an hour today. Don't waste it. Okay? Use it wisely. You've got a lot of stuff to do.